So last video you guys about Lorentz force, right? So Lorentz force was F is equal to Q into E plus B cross B, right? Okay, now what we'll do is we'll just restrict ourselves into one of the cases of a Lorentz force. Okay, that is, suppose let's say we have a charged body, okay, and we have a magnetic field, something like this. So as you can see in the figure, that's how the magnetic field and the charge is. Alright, now what happens is, let's say the body starts moving. Okay, so the body starts moving in this direction. See, it's moving in a circular path, right? Now what we are trying to calculate is what is the force on a charged body if it's moving in a circular motion in a uniform magnetic field. I'll repeat that again. So what we are calculating is what is the force on a charged body in a uniform magnetic field which is moving in a circular path. Okay, so let's try to derive it. So it's a very simple derivation. See, what we have is, we have the magnetic field to be B, charge to be Q, and then let's say the velocity of a charged body, let it be V. Okay, let it be V. Okay, now here, see, the magnetic field and the velocity, they are perpendicular to each other. Correct? They are perpendicular to each other. Now, since they are perpendicular to each other and it is following a circular path, correct? It's following a circular path. Now, this basically, how we get to know it is a circular path is by Fleming's left hand rule. Okay, so Fleming's left hand rule, let me repeat what it is. See, Fleming's left hand rule, the thumb finger, like when you extend three fingers which are at 90 degrees to each other, the thumb finger represents the force, the index finger represents the field, and the middle finger represents the current. Okay, in this case it's not the current, it's basically the charge. Okay, so force, field, current. This is basically the left hand rule. Alright, see in this case, now, see, imagine you have a circular plate kind of thing. Okay, you have a circular plate. You are placing the plate on the table. Okay, from the bottom of the table to the top of the table, there is a magnetic field which is there. Okay, and on the edge of the plate, that's what we call as the rim of the plate. Let's say, you take a marble and then you push the marble. See, that is basically the velocity of the charged body what we have here. Correct? So we have force, field and the current. So in this particular case, so the field is up and this is how the current or the charged body which is moving. So we get a force in one direction. Right? So you're going to get the force in one direction. Now the same thing if I do it in a diametrically opposite point. So both the forces, they are concentrated towards the center of the circular coil or the circular loop, you can say. Okay, so both the forces are acting towards the center, one common point, the center. So what happens is, suppose let's say we have a charge at some particular charge Q in a uniform magnetic field moving with the velocity of V, it forms a circular path. Okay, so whenever we have circular path, centripetal force comes into part here. Correct, centripetal force. So according to Lorentz force, we have F is equal to BQV sin theta, and centripetal force is F is equal to mv square by r. So we equate these two. Okay, now if you equate these two, now what is the angle between velocity and the magnetic field? It's 90. So we have BQV is equal to mv square by r. Correct? So since we have BQV is equal to mv square by r, now here we try to calculate what is the radius of the particular path. Okay, the radius of the particular path. So make sure that r is the subject of the formula. So we have BQV equals mv square by r. Vv gets cancelled. Right. So r is equal to mv divided by bq. Correct. So since we have mv divided by bq, now what we can conclude from this is, as the velocity of the object is increasing, the radius is also more. Okay, this is one part. The other part is, suppose let's say the mass of the object is very high. If mass is high, then radius will also be very high. Okay, and then if the magnetic field is very strong, like very strong, then the radius becomes very small. Okay, so this formula we are going to use for a machine called as a cyclotron, which you will be seeing in another coming videos.